Welcome everybody. Today it's my pleasure to have Professor Pete Schloerb with us. Pete is a professor at UMass, where he's also the director of the LMT at from the UMass side of things. And just a brief, couple of brief things about Pete. He obtained his PhD from Caltech in planetary science. And one thing I was very impressed about while reading his CV is that he has an asteroid named after him, asteroid 1973. So maybe you can ask him how to get an asteroid named after you during the talk. And today he will be telling us about the work he's been doing at the LMT in order to reach data observing with the telescope. And yeah, I would just like to say thanks, Pete, for giving this talk, and please go ahead.
Okay. Thank you very much, Pedro. Let's see. Okay, so it's great to be with everybody today. I've been enjoying talking to Pedro about your Lassie project at Green Bank, and at one point in those discussions, I foolishly said something like, "Oh, well, you know, if you ever wanted me to talk a little bit about what we're doing on this topic at the LMT, just ask." And then Pedro asked, so here I am. What we're going to talk about today is a project we have underway to try to take the LMT, which currently operates only at night, at least, and move into the daytime operation. So I'm going to turn this pointer on. The cover slide here is a picture of the site, mountaintop site with the LMT. Okay, so in the talk today, I'd like to, since maybe you're not up to date on the LMT, I'd like to tell you a little bit about the telescope, and then move to the question of the thermal behavior of the telescope, and talking about that. I'm going to show you how one of the things we've been doing to try to understand surface deformations at the telescope, and some of those measurements. Then I'll turn to the idea of how you go about managing these problems and what do you do about them as astronomers. And finally present an idea that we've been developing, which we call a laser truss for real-time measurement of the surface. So first, to talk about the status of the telescope. Of course, LMT is a 50-meter diameter radio telescope. The operational wavelengths, we aspire to get into the 345 gigahertz band, so we'd say 0.85 to 4 millimeters is the wavelength range. Telescope has an active primary surface. And at the moment, we have achieved something like 100 microns RMS over the surface, but we hope to be able to get to 80 microns RMS, and you'll understand what the plan is there as we go forward. And then finally, pointing accuracy, defined basically as relative offset pointing accuracy, is about a second of arc at this point. So where are we located? We're located in the country of Mexico. The telescope was built there in the state of Puebla. The mountain that we're on, which is visible over here to the right, is visible over here on the peak to the right. That is the mountain Sierra Negra. It's an extinct volcano. And we're located at 15,000 feet altitude. Of course, over here to the left is the tallest mountain in Mexico, which is called Pico de Orizaba, which is quite a sight. We have a couple of important support sites. Of course, our sister institute in Mexico, the Instituto Nacional de Astrofísica, Óptica y Electrónica, or INAOE, is located in the city of Puebla, about a 2-hour drive to the west of the telescope. And we have a small base camp in one of the towns down at the base of the mountain. We're going to talk a lot about the surface, so let me just introduce some aspects of the surface. The surface is composed of 180 segments, and each segment has 8 what we call subpanels on it that are aligned in the laboratory, and then the whole segment is installed on the antenna. There are 5 annular rings of these segments. For a long time, we operated the telescope using only the inner 3 annular rings out to a diameter of 32.5 meters. But in late 2017, we completed out the surface to the full 50-meter diameter, and so that's what we're looking at. That's what we're using today. So here are some measurements of the effective area of the surface. We've done this in kind of a funny way and corrected for receiver coupling, primarily so we could put this one continuum point on here for the Aztec instrument and have everything on the same scale. You can see that basically the surface RMS matches a model pretty well of around 100 microns. But we think based upon looking at sort of the residuals to fits of the surface as we do the surface setting, we really ought to be able to reach 80 microns. And the reason that we think we have not reached 80 microns is that we're limited by thermal deformations of the surface, which occur during the night while we're making the measurements. So part of our motivation for understanding the thermal behavior of the telescope is to improve the telescope surface setting. The LMT is fitted out with various instruments, and I have my list over here and some examples. We have the redshift search receiver, which is an ultra wideband receiver for the 3-millimeter window. It covers the whole region from 74 to 111 gigahertz all in one shot at about 30 megahertz resolution. So it's great for looking for highly redshifted CO lines in distant galaxies. And here's an example where we're picking up the 3 to 2 and 4 to 3 CO lines in the spectrum. We also have the focal plane array that we used for many years at UMass, which is called Sequoia. And here are some obligatory pictures of the Orion molecular cloud. The National Astronomy Observatory of Japan has provided a 2-millimeter receiver, which they call B4R, so it's the ALMA band 4 receiver, basically. And with this comes a wideband spectrometer that's kind of interesting. And some examples, again, from everybody's favorite target, Orion. And finally, we have built a dual polarization 1.3 millimeter SIS receiver. This is a spectrum I took of Comet Wirtanen, looking at methanol of 243 gigahertz or so. And then finally, of course, LMT participated in the imaging, the first image of the black hole by the Event Horizon telescope. And we're very proud of that. But we're not done, because coming soon we have an instrument which is called Toltec, which is a 3-color camera and polarimeter covering 2, 1.4, and 1.1 millimeters wavelengths simultaneously with about 10,000 pixels. And that's going to be a really revolutionary and remarkable addition. We also have coming a focal plane array for the 1-millimeter band, which is called Omaya. Both of those should get installed on the telescope within the next year. Toltec probably going down there sometime still before the end of the year. And finally, we have received funding to develop a dual frequency receiver whose primary for the 230 and 345 gigahertz bands, whose primary purpose is going to be to help the Event Horizon telescope as we try to move that instrument towards doing dual frequency observations, the LBI observations. So the biggest question I used to get in presentations was, can I use the LMT? And usually I would give a very somber answer about that because, you know, something along the lines was, well, you know, UMass paid to build it and we pay to operate it, so why would I give you any time? But now the answer is yes, absolutely. And that's come about because of the award of an MSIP grant recently announced to UMass. The MSIP grant will allow US institutions to access 15% of the time on LMT. And this will be done through the normal proposal review process that we have at LMT. And the next opportunity is going to get announced sometime at the end of October. The observations are going to be carried out in a Q-scheduled service mode and by operators. And so nobody actually has to go to the telescope, but you will be able to participate remotely in the observations. You won't be controlling the telescope, but you will be able to interact with the operator. There aren't any requirements in this program for any kind of collaboration with the LMT partners at UMass or in Mexico, so people can put in their proposals and try to get their observing time. One other thing we aspire to do is to provide basic reductions of the data to what the community now understands as science-ready data products. We're developing those pipelines. That's an important part of the MSIP award, and we think that'll make life easier for everybody. So today what I want to get to is next is to talk about thermal stability of the telescope. We've been limited so far to operations under nighttime conditions when the temperatures are stable. But we'd really like to expand the number of available hours because first of all, we'd like to get more telescope time for our users, and second, the ability to participate in VLBI will be enhanced if we can observe into the daylight hours and help extend all of the UV tracks with telescopes, for example, in Europe and farther west. So the limitation here is obviously how do we correct for thermal deformations, and that is the goal of the next talk. But just to show you, there's some value in going to daytime. Over here on the left are our opacity statistics over the year for the nighttime, and we have a dry season, which is sort of the winter months. And there's really, if you look then at what's going on, at least in the mornings at the telescope, there's really not any difference between what's going on at night and what's going on in the morning in terms of the opacity of the site. So we can pick up at least several extra hours, and you know, even given the high dry site, even the afternoon when sometimes the clouds can roll in is not so bad. So there's quite a lot of observing time to be had if we can push into the daytime. So let me talk a bit about the thermal behavior of the telescope. Just to summarize a few of the pieces, of course, we have the active primary surface and the surface segments that I pointed out in the previous picture. And then, of course, this is an Altaz mount, so we have an alidade and then a whole structure that rotates in elevation, including these counterweights, which for some reason the German designers like to refer to as ballast cantilevers, and so on. And then, of course, we have the backup structure of the antenna itself, which I was often referred to as the bus. And finally, another important component is the support of the secondary mirror, the tetrapod, or the legs. All right, so when the LMT was designed, the designers considered a number of thermal design cases. For example, one design case they considered was a front to back gradient within the backup structure, and a relatively small gradient can lead to a big change in the RMS of the structure. They also looked at what would be required to change the shape of the surface if there was a difference between, say, the backup structure and everything else. which in this case, a 5-degree difference between the backup structure and everything else in the system leads to about 60 microns in a relatively complicated pattern. And then finally, if we take everything that rotates in elevation and make that 5 degrees different from the alidade, then you can see that we get an interesting pattern here, but a relatively small change for a 5-degree difference. So the takeaway from the design work was that that small gradients within the structure can change the shape of within the backup structure can change the shape quite a lot. It takes a pretty big temperature difference to change the shape of the antenna. Antenna surface, big difference between the backup structure and the rest of the structure to change the shape. Because of the backup structure susceptibility to temperature gradients, the original design of the telescope called for us to put a system of ventilators within the backup structure to blow air around and try to homogenize, take down the temperature gradients. So let me spend a minute characterizing what the temperature behavior actually is. We can look at the, so basically we have a system of temperature sensors. We're in the process of upgrading this from 64 to 256 sensors as we get more serious about the problem, but they're located all over the structure. And we can look at the temperatures of different parts of the structure. These are all structural temperatures, so looking at temperature differences between the middle of the backup structure and the alidade, the counterweights, and the big central cone that forms the center of the backup structure, and also difference between the counterweights and the alidade and so on. And you can see that. So maybe it's not so easy to see. The scale here is 1 division is 2 degrees. So you can see that we get maybe 1 degree differences going in here, but nothing like the 5-degree differences that were necessary to drive drive big surface deformations. On the other hand, we can look at what's going on within the backup structure, and you can see quite a lot of temperature variation. Again, this is 2 degrees is 1 division here. So the red line here is the difference in temperature between sort of the inner part of the backup structure and the outer part. And we get top-bottom gradients when the sun is shining on the surface. And we can even get gradients right and left across things depending on the direction that the sun is shining. So let me, it's pretty clear that these are going to be important differences and that there's things that we have to deal with. Without belaboring the point, this can get really complicated as the sun shines on different parts of the antenna. So here are 6 curves corresponding to what's going on in 6 radial directions around the antenna surface as the solar illumination changes, and as we move when we move the antenna to new positions, and the solar illumination changes. And so there's quite a lot going on here. You wind up driving gradients in temperature across the dish because one side is illuminated and the other side isn't. The weather can form a problem. All of a sudden, at some point here, clouds moved in for a short period of time, the solar illumination went away, temperatures dropped, and you can see things going on there as well. So it's a complicated business what's going on when you illuminate one of these guys with sunlight. And that's also true when we look at the behavior of the secondary support structure. At the same time, we drive quite a big difference in the temperature, quite a big change in the temperature of that thing during illuminated daytime periods. And of course, if the sun goes away, as it did right at this time, things cool down quite quickly. Okay, so so another thing we've looked at is what's going on within the surface segments themselves, and the segment fabrication team led by my colleague Dave Gale, Illinois, have spent some time making measurements of the thermal behavior of the segments on the surface. And here's the sort of thing that happens. It turns out that our surface segments are the same ones in the European Alma dishes, which basically absorb sunlight pretty well. As a consequence, the surface gets very hot when the sun shines on it. And that can be seen over here. This orange line is the temperature of the surface subpanel itself, they get really hot. The rest of the structure, because we have insulation on the back of those guys, doesn't change by very much. It does go through diurnal cycles here. We can take a little closer look at that by blowing up the scale here. You can see that basically at night, all parts of that structure settle down and to a state where there are no gradients between the parts of the structure. The red line here is the backup structure element near the structure. And that, okay, during the day when things get really, really hot at the surface, there are some gradients driven, but not, it's not so bad. And design studies of this structure show that if you can basically raise the temperature of those surface subpanels to pretty high values compared to everything else, and it does not affect the shape of the segment by very much. So we think that the design of this will allow us to observe during the daytime, even though those panels can get pretty hot. Well, let's talk about measuring measuring thermal effects. And the way we've done this, particularly motivated by the fact that we think thermal gradients are a problem for setting the surface, has been to use photogrammetry, which is the technique we use to set the surface, and basically make repeated maps to try to see what happens during the night. And here's an example. So each of these is an individual photogrammetry map of the surface of the LMT during a particular night. This night we got 2, this night we got 3, one night we got 7. It takes you know, about an hour or so to get the measurement, so you know, we get what are not exactly snapshots, but we do get a view of what's going on during the night as things go on. And the thing that's obvious when you look at these things is this particular pattern, which, if you know Zernike polynomials, is a familiar pattern. It's the vertical astigmatism Zernike polynomial. And if you know antennas, then you know that this is a pretty common pattern on antennas. You can think in many ways the LMT and the Huron 30 meter are kind of sister telescopes because they were designed by the same firm, and they both have this as one of the major deformations that occurs in the face of thermal error. So we've gone on and taken this set of data and fit to different sets of Zernike polynomials. If you don't know what they look like, well, here's a set of Zernike polynomials. These have the advantage that they're orthogonal over the aperture. And the idea has been to try to understand, okay, well, where are the dominant modes of deformation that we see, and you know, and can we understand relationships between the different parameters, do any exist, and so on. So the first thing you can do is you can take each of the maps and you can ask yourself, what is the RMS that remains after I remove a Zernike polynomial of a particular order? So if I only take things out to the best fit parabola, I get quite a range of RMSs here, and that's basically because of the vertical astigmatism term. When I add the vertical astigmatism term, a lot of this big stuff goes away, and so my range, that's number 5 here, my range is quite small, but I'm still got over 100 microns RMS of error. As I add more and more Zernike terms, the errors improve until eventually we reach asymptotic behavior somewhere after about 15 terms or so, we wind up at about 88 microns, which I think is the residual error in the setting of the individual segments, which in principle we can remove if we can measure it well enough. Okay, so the thing to keep in mind here is that once we get above about 15 terms, we've taken out most of the problem. You can look at the magnitude of the Zernike coefficients for each of these terms. So there's quite a big magnitude and range for the vertical astigmatism term. After you've taken that out and the focus term out, then there is some measurable and some of these other terms become measurable at some level, and it's interesting to see the occasional oddball here with one of the coma terms. Once we get beyond about 15 terms, then the magnitude of these coefficients goes away. So basically, what we can see is that the photogrammetry is measuring the shape of the surface, and we can measure its response. We've got an idea of the major deformation, and we can then, which is the vertical astigmatism. And if we could measure these low order functions, we'd be able to remove the effect. Now, just for fun, we looked hard for various correlations between the coefficients, and there are hardly any. So I'm going to show you the two that actually exist. There is a correlation between the defocus term and the vertical astigmatism term, which is interesting. There's also a correlation between the vertical quadrifoil term and the spherical aberration term, which is interesting. But that's pretty much it. We don't really find, like there's some mode expressed by a linear combination of terms that pops out as an underlying shape principle. There is, however, a pretty good reason to believe that this is a thermal deformation problem, and that is that if you just pick one of the things we measure, the radial temperature gradient in the structure, that is correlated with the vertical astigmatism number, and so you get an idea that in fact that's what's driving these things. Okay, so let's talk about, we've got thermal distortions. What do we do about it? Okay, so the one thing is that you try to minimize thermal gradients the best you can. We have thermal cladding insulation on the outer parts of the dish to try to knock down the temperature variations that occur. And we are presently working on, and we have funded a system for ventilating the backup structure as called for in the original design of the telescope, and that's something we hope to get in within the next year or so. Another strategy people use is they measure the temperatures over the structure and try to predict the deformations and make corrections. That's part of why we're going to install 256 sensors on this. The advantage, and of course one hopes to find good correlations that will allow us to make corrections. But I think that there's a limit to how well you can do with that, and so that's pushed most of us that have big telescopes into trying to do astronomical measurements of one sort or another. Of course, we all focus up and point the telescope periodically. And then I know at Green Bank Telescope, you use out-of-focus holography, and we've experimented a bit with that ourselves to try to make these measurements. Another thing that we do that is like out-of-focus holography, which I'm going to show you some examples of, is if you know what the worst distortions are on your dish, you can actually just try to optimize for those. So in our case, we know the vertical astigmatism term is really important. With the active surface, we can actually measure that and remove it. It's kind of like a one-term out-of-focus holography experiment. And then finally, there's the issue of real-time surface measurements, which I'd like to tell you a little bit about our concept. So here's an example this is something we now do routinely at the telescope and have done for many years. We actually distort using the active surface. We put the telescope in different shapes using the Zernike vertical astigmatism coefficient to drive the surface into those different shapes. And we make measurements of the gain of the telescope at these different in these different positions. And you can see down here, these are made with the Aztec instrument, which was an imaging instrument, but then led to some, leads to nice pictures as you do this. You can see the effect of basically tuning up the astigmatism parameter and finding the best fitting value. And this is, as I say, something that we do now routinely. Here's some measurements we made as we've been trying to study the effect of daytime measurements. Here is our friend, the Orion SIO maser. These are measurements made with the Sequoia receiver. I foolishly made all of these plots so that they auto-scaled, but you'll note the scale here, this is 500 degrees for the one on the far right, and this is 100 degrees here for the one on the far left. So that guy would be only this guy here. So quite a difference in the flux. And the pictures down below show beam patterns that we made in each case, and you can see there's quite a difference in the beam pattern as well. And if you're a beam pattern aficionado, you probably recognize that we've got an astigmatism network here. So over here, these are the values that we cranked into the surface. Over here are the typical nighttime values. And you can see that basically the performance isn't very good, but if we optimize those guys, we actually get a good beam pattern. I ran out of room on the slide, so I can't show you the other side, but we ran out of room. But basically, we were able to recover almost all of the antenna gain that you see at night on the same object. To put this in context, these things that look like windows are the vertical astigmatism coefficient determined from the astronomical observations. And here's the point I just showed you down here at 1200 microns or so for the magnitude of the coefficient, as opposed to a few hundred, maybe 300 microns for these guys. So there's a big effect that occurs during the daytime, and in this one mode that we found is important for measuring, is an important mode of deformation under thermal stresses. So now let me tell you a bit about an idea we have for trying to make real-time measurements of these surface deformations. And that is what we call a laser truss technique for making real-time measurements. Of course, you at Green Bank are familiar with the notion of a terrestrial laser scanner, like the Lassie project uses, and that's one way you can go about trying to measure the surface deformations. But another way you can do is with this concept that we call a laser truss. If you measure the distances between points on the surface, then it's possible to reconstruct what the shape of the surface actually is. The particular device we're using is something from a company that used to be called Etalon. The name of the product is the Absolute Multi-Line System. It's basically an approach that uses standard optical fibers to feed a laser signal that is bounced off of a retroreflector and back, and compare it to a reference laser signal that arrives at the same thing, and that's how the measurement is made. It's a very accurate measurement, something like a half a micron per meter in accuracy. You can buy these things if you have unlimited money, you can buy these things in very large numbers of channels. We've discovered that it gets pretty expensive as the number of channels goes up. But for us, it looks like a good deal because these things go out to 30 meters or so. And as I say, it uses standard optical fibers and is pretty robust. People are looking at this in astronomy, and here's an example. You can, if you peruse the SPIE publications, you can find nice examples. And here's an illustration of one such test with the VLT trying to figure out, locate the secondary mirror. These devices are being looked at and built into the designs of a lot of the big next generation optical telescopes, and it's in use actually at the Large Binocular Telescope in Arizona. So what's the approach for the LMT? The idea is that we would make a series of point-to-point measurements on the surface and use that data to estimate the Zernike polynomials. We know we want to get out to about 15 terms, which means I better make about that many measurements. And we have an error that would be useful of something like 10 microns, particularly remembering that the vertical astigmatism coefficient can be hundreds. That seems like a pretty good thing to do. The other thing we can do is to measure the secondary mirror position with respect to the surface. There, the criteria are pretty tight. You need to know to keep things well under an arcsecond. You need to keep these guys under about 10 microns. Okay, so let's take a look. Here's an arrangement of 16 measurements of point to point, basically from the inner part of the surface to the edge and to a point out in the fourth ring of our antenna. I can simulate what the measurement would look like with Monte Carlo simulation and this little corner diagram. So it shows the error distribution along the diagonals and the correlation in the off-diagonal elements. These particular charts were made with 10 times the nominal measurement error, which means that with the vertical astigmatism and the nominal measurement error, I can get to 8 microns RMS, which seems pretty good when you consider the magnitude of the thing we're trying to measure. Here's just a formal summary of all of that. If you take the errors on all the coefficients and put them together and try to estimate the error of the reconstruction of the surface, we think we could get 30 microns. Subreflector measurement is similarly is straightforward, and basically I followed what they do on the big optical telescopes, except I use more measurements. So here's 8 measurements. We've got good points to anchor these guys down at the base of the tetrapod legs. So with the 8 measurements and 6 degrees of freedom, I can again see what kind of accuracy I could get with the nominal measurement accuracy. We could measure the secondary mirror of something like 10 microns, which translates into a pointing error of under a 1/10 of a second. And of course, you're getting the z-axis measurement as well, and the 11 micron error on that means that the gain change due to secondary misalignment is much less than 1%. So why do we like this approach? I mean, most people, when I tell them about this for the LMT, says, well, I understand that the Green Bank telescope is using this other approach. Why aren't you doing that? So let me start with, why aren't we doing that? Well, one thing is that on the Green Bank telescope, there's an obvious place to put your laser scanner, but in our case, there is no obvious place to put that laser scanner. And then the other thing about our telescope is that it's a pretty forbidding environment, and not the sort of place where you want to, hang sophisticated pieces of equipment upside down out in space someplace. And so that was part of what drew us to dealing with the laser truss approach here. First of all, you can set up your laser, you can set up the base station for this in a nice safe place, and then the fibers themselves can go out to kilometers from the base unit, and they're just normal fibers, so it's quite a robust system. We can put, the system involves active transmitter and passive reflector targets. We can put those transmitter targets in places that are easy to get to, and we can put those passive reflectors, for instance, around the secondary mirror, out in places that are difficult to get to. And then another feature about this is that to harden things up, the lasers can actually work through windows. they're used in, you know, windows going into vacuum tanks and cryogenics and stuff. And so that means that it's possible to build a structure around them to enclose and protect them. And so we actually like this in terms of a lot of the operational features. So that's a bit about what we're up to and in these things. I'm sorry if I've gone a little long, but I thank you for your attention as we gaze out on Pico de Arizaba and Sierra Negra, where the LMT is located. Thanks a lot.
Thanks a lot for the talk, Pete. It was very interesting. We don't have much time for questions because we should leave the room at 1. But if there are any questions, we can take a couple before we leave.
This is Ryan. I have a couple hopefully quick questions. The first is with the laser system you're using, is there any kind of like a maximum path length for the actual laser to traverse before you start to get into errors, not just like in the range, I guess, but like from, you know, atmosphere scattering. And then the other one I'll just ask real quick is, what are the disadvantages? Because it sounds like a really nice approach compared to like the TLS system we're using. So what are the disadvantages?
Okay, so I'm not entirely certain what the maximum distance is. I mean, obviously, if it's foggy or something, then you wind up with a problem because you have to be able to, you know, one unit has to be able to see the other and things like that. So, but anyway, I mean, the scales at the scales we're looking at were within the envelope that they've done tests. The with regard to what are the disadvantages? Well, okay, so one is that we have to, we still have some engineering to do in terms of how do you build the protective box and sit it on the surface of the antenna in a way that it won't get knocked off the first time ice slides off of the that's accumulated on the surface slides off. I mean, so I would say there's a number of these kinds of practical things that I might be worried about. I think it's a bit expensive. I mean, compared to the terrestrial laser scanner approach. I mean, the basic device we're looking at is something like $500,000, so that's something to be considered. I mean, it's great if you've got $1 billion optical telescope and you need to know where the secondary mirror is. That doesn't seem like very much money, but it's a lot for us. You know, so I guess those would be some of the disadvantages. There's probably a lot more that I haven't thought of.
I think we have time for one more question.
Well, let me just say that the reason I'm giving this talk is I'm kind of interested to hear people's reactions. So, you know, please feel free to drop me questions or you know, send me an email saying, Pete, that's the dumbest idea I ever heard of. You know, I'd be you know, happy to discuss that with you. One of the reasons that I've been very excited about talking to Pedro and hearing about the Lassie project is that, of course, the LMT and the GBT have a lot in common and many common problems and areas we can work together on, and I think this is certainly one of them.
Yeah. If just contact Pete if you have any comments. Personally, I don't think it's such a crazy idea. It sounds like very reasonable. And thank you very much for giving this really nice talk, Pete.
Well,
thanks everyone. Thanks everyone for joining, and we'll see you next week.
Thank you.
Thanks, Pete.
Thanks, guys. Stay safe up there.